Hello, welcome to this video where we're looking at polar double integrals. Double integrals done in polar coordinates. In the previous video, we laid down the groundwork, found out how to do it, how it works, why is there an extra factor of r from the Jacobian. And then in the video after that, we looked at two examples. I would consider them medium examples. And now we're going to look at a difficult example. And then hopefully we'll have time to fit in another example after that. All right, our job in this question is to evaluate another double integral that's given to us in terms of Cartesian. So it seems just like the other two examples, but it's the region that makes this much more difficult. How do you get the region? Interior bounds go with the interior variable. Exterior or the outside bounds go with the outside variable. And so we have y's that are between the radical and 0 and x's that are between 0 and 2. The issue is this radical. You see, the other two examples had the unit circle and they were straightforward. But this example has y equals the square root of 2x minus x squared. We have to figure out what that is in terms of polar. And so one technique is just a straight substitute. We know that y equals r sine theta and x equals r cosine theta. You could just straight substitute in. Another technique is to manipulate it a little bit, square both sides, and then maybe substitute it, or maybe substitute it at some other point. But we're going to do it exactly as it is. Plug in right now, r sine theta equals to the square root of 2 times r cosine theta minus the r cosine theta squared, quantity squared. And what do you think we're going to do algebraically is, to simplify this, we're going to square both sides. We'll get r squared sine squared. We'll go ahead and square the r cosine inside, square each piece there, and add over the r squared cosine squared because, you know, cosine squared plus sine squared is equal to 1. So that kind of gives us to us once we factor out the r squared. So we have r squared is equal to 2r cosine theta. If we divide by r, we have to consider, well, maybe that r could have been 0. So let's not divide by r. Let's move the 2r cosine theta to the other side, factor out that r, and be left with r equals 2 cosine theta. Yeah, either r equals 0 or r equals 2 cosine theta. These will be the bounds on r. Okay. X's are going between 0 and 2. We got to be able to get a graph of this. All right. Now, the circle r equals 2 cosine theta is not centered at the origin. R equals to a constant are circles centered at the origin. If you have r equal to a constant times cosine, it's a circle that's centered on the x-axis. And it has a radius that is half the multiplier on cosine. And so we move over half that unit. Our center moves from the origin over to 1 in this case. And then the radius is equal to 2. I'm sorry, the radius is equal to 1. The radius is equal to 1. Sorry about that. All right, so x is greater than 0 and y is greater than 0. That puts us in the first quadrant. So we're talking about the first quadrant. And in the first quadrant, you know, thetas are between 0 and pi over 2. Got to double check and make sure everything's working out. But if you went and plugged in theta equals 0 to that r function, 2 cosine theta, you'll be at 2. And then theta is going to decrease. When you plug in pi over 2 into that guy, you'll get r equals 0. So from 0 to pi over 2, this particular circle is only the upper half. When you move away from a circle that's centered at the origin, what happens is the circle actually gets completed faster than 2 pi. This circle gets completed by the time you get to pi. And so that's our region. And with this, then, we draw in the bounds. We radiate outward from the origin, put circles on the ends. That's the upper limit inside and the upper limit outside. Lower limit inside, lower limit inside, and upper limit inside. The two circles there. 0 is the lower limit inside. And this function, r equals 2 cosine theta, is the upper limit inside. And we know the theta bounds. Just because you're in the first quadrant doesn't mean that theta is between 0 and pi over 2. So that's why we had to check it. So we know the bounds now. Now we need to convert the inside. Square root of x squared plus y squared, that's an r. dy dx, that's an r. dr d theta. And r's go from 0 to 2 cosine theta, and thetas go from 0 to pi over 2. We're integrating r squared to start out. R goes first. The r is going to give you r cubed over 3 for the antiderivative, or 1/3 of r cubed. Here comes the issue. You have to cube 2 cosine theta. And doing that gives you 8 cosine cubed. Take the 8 and the 1/3, take it outside, and now you have to deal with cosine cubed. 0 gives you 0 for this. How do you integrate cosine cubed? We saw that when you have cosine squared or sine squared, you use the half angle identities, but when the power on cosine or sine is an odd power, you don't do that. You factor out one of them and you convert the other two. I factor out one cosine and I still have 2 more left. I have to convert them using the Pythagorean identity, not the half angle. So cosine squared is 1 minus sine squared. What this does, this sets up a nice u sub for you. If you let u be equal to sine, then the cosine theta d theta is the du. And you'll be looking just at 1 minus u squared, the function that you have to integrate. Who integrates to u minus u cubed over 3. And you can trade back in what u was. U was sine theta minus 1/3 of, so we have sine theta minus 1/3 of sine cubed. Our job, put a pi over 2 in and put a 0 in. But sine of 0, sine cubed of 0, they are 0. So pi over 2, sine of pi over 2, that's a 1. So 1 minus 1/3 on the inside, 8/3 on the outside. That's a 2/3 on the inside of the parentheses. Altogether, 16/9. That was a tough one. Went through it rather quickly, but doable if you find the region, make sure you have the bounds right, convert the inside, and execute the r theta integral. All right. Let's go ahead and try to fit in this next example. So first off, before this example 4, I want to talk about how you can find area of a 2D plane, area in the xy plane of polar using a double integral. We saw in the last set of videos that if you have a double integral over a region in the xy plane and your integrand is a 1, that actually calculates the area of that region. Now, in polar, dA becomes r dr d theta. And so, double integral with an r dr d theta represents area in polar. Okay. All right, great. 8 minutes. I think we could do it. So, we have this function. Example 4 is the function r equals 2 sine of 2 theta. It's not a circle anymore. When you double the angle, when you put a multiplier on the angle, we get away from circles. And so r equals double the sine of twice theta represents one of the rose petal curves. And we're constricting ourselves to only use thetas between 0 and pi over 2. If you need to, what you can do is just, pick 0, pick like pi over 3, pi over 4, pi over 6, and pi over 2. Plug them in and see what r is. And what happens is you can trace out the function that way. This is one petal of a 4-leaf rose. And we're going to find the area inside of one petal of this particular function. You start at 0, r is 0. You go out to pi over 4, r is 2. And then you come back down to pi over 2, r is back down to being 0. And so we have the area being equal to the double integral from 0 to pi over 2, and then radiate outward from the origin. The lower limit is 0, the upper limit is our function. That'll be our area in polar. Integrating r dr d theta. That's the replacement to dA, the original integrand that calculates area is 1 dA, and now we have 1 r dr d theta. Okay, you might have done integration in polar before, but you started as a single integral back then, where you said the integrand has to be r squared over 2. Here's why the integrand is r squared over 2. After this first integral of r, you get r squared over 2, and then you put these, you put the function in 2 sine 2 thetas, which is square. You square to 0, you get a 0. And so the 1/2 and the 4 from squaring the 2 becomes a 2 on the outside. And here's sine squared again. when you have no odd powers present, you just use half angle identity. But if it's already double theta, then when you go to double the angle, it's going to be 4 theta. Okay. And so we replace sine squared 2 theta with 1/2 1 minus the cosine of 4 theta. The 1/2 and that 2 can cancel out. And now we're just integrating 1 minus cosine 4 theta, getting theta minus 1/4 of sine of 4 theta. Put a pi over 2 in, put a 0 in. 0 gives you 0 for both of these. You get a pi over 2. And then if you take 4 times pi over 2, I think that gives you a 0. So, yeah, the answer is pi over 2. All right, great. Sorry, I went over the 10 minutes. I want to do a couple examples. Area and polar will be the attack for the rest of these videos that I have coming. It should be about 2 more videos where we really dig into area and polar. And so I will, I'll stop the video now. Thank you for watching. My name is Nakia Rimmer. And if you need help with multivariable calculus, please reach out to me. Comment down below, like and subscribe. And reach out to me through my webpage if you need resources, lots of extra problems or lots of solved problems, midterm problems. You need that, you can find it on my website. All right, thank you for watching, and I'll see you in the next video.